Yep. Thanks very much, Scott, and yeah, for twisting my arm to give the talk here as well. And thank you everybody for coming. It's really nice to see some familiar faces and some new faces. Yeah, like Scott said, it's been I've worked in New Zealand and did my PhD here, and then always kind of been a little bit divided between working in Germany and then back in New Zealand. And feel really fortunate at the moment to have an opportunity where I have the bulk of my position at NIWA, so back in Wellington with the family and everything, but still have a bit of a connection to GEOMAR in Kiel. And so the talk that I'm giving here and what I want to talk about summarizes work that a lot of the focus has been over the last sort of 3 years. Over there, well, actually, we collected the data in 2019, but as you all know, it takes quite a long time to make progress. But yeah, what we've been working on there is in particular focusing, like Scott said, in the Aegean Sea and looking at some of the geohazards there related primarily to volcanism and to tsunamigenesis related to volcanism there. So I'm going to just go ahead and start talking about that, hopefully. Whoops. Yeah, I thought to set the scene a little bit, if we cast our minds back a couple of years to the Hunga Tonga Hunga Ha'apai eruption. This was something that is etched in our minds pretty clearly, because this was a really enormous event felt around the world. The impacts, the atmospheric waves basically that were generated as there was this huge explosion, then a 50-kilometer high vent into the atmosphere, and then these atmospheric waves that traveled around the world multiple times. And it was really unprecedented in terms of the observations that were made from being, in this modern age, to be able to see what one of these kind of eruptions really looks like. And for us, it really brought home kind of the relevance of the work that we were doing in the Aegean Sea, where we were looking into the geological archive of these kinds of processes, but we could see something that had happened, right now. So that was kind of the far field thing. Locally, it was devastating for Tonga on the main island. Down in the bottom there, we've got on the bottom left a photograph of the coastline showing the pristine kind of environment before the tsunami hit. After the tsunami hit, there was quite a bit of devastation there. Unfortunately, there were 7 lives lost and about an additional 20 injured, and something like $90 or $100 million worth of damage. Up the top, you can see how the island basically evolved. So on the left-hand side, there is what it looked like before that eruptive process kind of started in 2020. And then in early January of 2022, the island was starting to grow as the magma chamber was basically feeding into it. And then a couple of weeks later, the whole thing, as we know, exploded, and we lost the island from sight above the sea surface there. So yeah, that's closer to home. And now if we go into Europe, in the Mediterranean or in the Aegean Sea here between Greece and Turkey, this is a part of Europe that is very seismically active. So the largest shallow earthquake of the 20th century was here, was the Amorgos earthquake of magnitude 7.7. So there's quite a lot of threat for seismicity in the region. Also, of course, the volcanic region. So what we have is we've got subduction of the African plate beneath the European plate, and in the Aegean Sea we have thinned continental crust that is basically then accommodating these volcanic centers, and in particular that there's this Christiana, Santorini, Kolumbo volcanic chain, which is highlighted on the left-hand side here. So do I give a pointer or anything, or no, just do it with the mouse, I guess, if you can. I don't know, can you guys see that mouse? Or yeah, okay. Yeah, so we have Christiana down here in the southwest. Santorini is obviously well known. It has something like 1 million tourists visit there a year, and then Kolumbo further to the northeast. And so the region from sort of the onshore archive, it's estimated that there've been at least 100 explosive eruptions in the last 350,000 years. So it's volcanically very active. And it's two of the better known ones there are, of course, the late Bronze Age Minoan eruption, 1600 BC of Santorini. So that was, one of the largest in the Holocene, estimated maybe 20,000 fatalities from that. And yeah, something with, one of those really global volcanic eruptions. Then in 1650 was the eruption of Kolumbo Volcano, so just a mini volcano really compared to Santorini, just towards the northeast there. That generated a tsunami, which affected the surrounding islands. It also led to about 70 fatalities on Santorini from the pyroclastic flows that spread across the sea surface towards Santorini. So yeah, there've been quite a few projects in the region, in the Aegean Sea, and with different motivations and different aims. One of the things that we were doing with regional 2D seismics was to try and understand the geological archive from Santorini, and in particular map out the deposits from the Minoan eruption. But I'm not going to talk about that this evening. What I want to kind of focus on is mainly around Kolumbo Volcano, where we collected 3D seismic data and we had the primary motivation of that was really to understand the geological history of Kolumbo, how it's kind of built up different cones through time, and to try and understand what the geological processes were behind the tsunami that happened in 1650. So that, and then there was kind of an advantageous little side study that we could do based on some well-imaged fault zones within the data, to try and get a better idea about interactions between the structures, so the faulting system, and volcanism. So there's kind of those two things. And I just wanted to split the talk up, so I've got enough to talk about in the first part, where I'll talk about local tectonics and the interaction with volcanism. And then maybe after that we can stop for a bit, any questions or anything, and then I'll get into the second part, which is kind of more about dealing with the processes behind the tsunami from Kolumbo Volcano. Okay, so this feels like an eternity ago now, because this was pre-COVID. Life was pretty simple. We went out, and this is a photo taken from one of my colleagues who was on the cruise from Santorini, looking out through the breach of the caldera. We had beautiful weather for about 3 weeks, which is ideal for collecting seismic data. So it was a really nice cruise. This is the ship that we sailed on. It was the second last cruise for that vessel before she was retired, and then became a rescue boat in the Mediterranean. So that's what Poseidon does now, basically. But yeah, so we had the privilege to be able to be on the vessel for the second last time. And like I said, we collected 3D seismic data. So what you can maybe just kind of make out in this picture here is over on one side here, there's looks like some kind of a marine mammal breaching the surface, but it's a paravane from the 3D system. So it's a trawl door that holds the whole seismic system in place, that we use to collect 3D seismic data. So I think I have here what this looks like in a sketch. We have the seismic source, so air guns behind the vessel, and they are towed at about 2 meters water depth. They generate an acoustic signal that travels through the water column, reflects off the seafloor. Part of it is transmitted and reflects off the underlying boundaries, and then we record all of that energy. And sometimes you do that in 2D and you just shoot one line, but the idea with this system is that you cruise around for 2.5, 3 weeks, around in circles, and collect a volume of data to be able to have a 3D, to look into the subsurface in 3D. Yeah, so that's what we did, and here you can see it basically from looking out from the stern of the vessel. There's somebody here from the ship's crew in a stressful job there, sitting on his deck chair, looking out the back and checking that everything's going okay. Yeah, the air gun is basically fired every 5 seconds or so, and yeah, and then we collect all of the energy in those streamers that are towed out behind the air gun, and they give us this image into the subsurface. Yeah, so after, like I said, we did that for, it took about 3 weeks, and luckily we had weather like I showed in that photo there before. Often that's not the case, and then you have to stop what you're doing and start again, and it's a bit of a hassle for 3D data, and sometimes it just doesn't work out because you don't have enough time, or you have just such major disruptions. But we were lucky that we had good weather and the system worked well. And so this footprint, this 3D box here that I've sketched over the top of the bathymetry here, shows you the data volume that we were able to collect over the top of Kolumbo Volcano. Santorini is here to the west, and I'll just show you if my video works, which it didn't last time, but I hope it does tonight. If we look at the data set and just start on the southwestern side, so on the red panel, and it'll just kind of migrate through, and you get a feel for what the data set looks like. So I'll just hit play, and you can see, so this is, yeah, moving. It's basically a 13-kilometre long section, and it's 3 kilometres in depth that way. And we have a resolution in the data set here of 3 meters, basically. So we have every 3 meters, we have a seismic trace that gives us this kind of sampling of the subsurface, and that's in both directions. So in the inline direction and also in the crossline direction. And so here is the crater of the volcano, and I'll get into some more of the details as we kind of go into the talk. But there are quite a lot of interesting things, and there's still a lot that we can kind of pull out of the data. We can see at depth it's really like polygenetic. There are a lot of different volcanic cones that have formed in the past, and then new ones that have exploded or been, some of them have been completely truncated by the 1650 eruption. But so this is the crater from the 1650 eruption, and the sediments, basically everything down to here, is part of that cone that was built up by the eruption in 1650, and also all of the material that's over on the northwestern side as well was all deposited during that event in 1650 over a space of a couple of weeks. Okay, so yeah, part one of what I wanted to talk about is a little bit about kind of local tectonics and volcanism at Kolumbo. And yeah, so I gave kind of a general introduction there before into the regional geological setting. More locally, we've got a lot of northeast striking normal faults, or northeast striking faults. There's I'll get into that in the next slide, a bit of dispute about the nature of the kinematics of these faults. But a lot of the existing studies basically pointed to these major horse grab and basin bounding normal fault systems that align together with the orientation of the volcanic centers, so Christiana and Santorini and Kolumbo, and then the Kolumbo volcanic chain, which is a chain of numerous smaller volcanoes that kind of extend further up towards the northeast. This is the 1956 earthquake that I mentioned at the beginning. So a normal fault mechanism, magnitude 7.7 on the Amorgos fault up here further north of Kolumbo. Yeah, and I mentioned some disagreement over the regional kind of fault settings. So there's a couple of quite recent studies, and the one on the left is mainly based on differential GPS data, but also with some gravity and magnetic data. And they have basically proposed a Riedel conjugate strike slip system around Santorini. It's quite hard to see in this plot here, but the slightly darker black line here is the coastline of Santorini. And so we've got these this northwest striking dextral strike slip fault and sinistral strike slip faults kind of oriented northeast. And then their interpretation of at least the local stress field around there with the extension direction, that's the sigma 3, being more or less east-west. And then a paper just 1 year after that is proposing from shallow seismics and bathymetric data, highly oblique rifting with an extension direction that's kind of northeast-southwest, and then dextral strike slip fault systems kind of all through the graben, but with some component of extension as well, as you can see, but like a predominantly strike slip. So these two papers are difficult to reconcile with each other and their interpretation of the structural setting, and they're also, both of them are difficult to reconcile with the earthquake, the normal fault mechanism from the earthquake a little bit further towards the north, and other studies as well that kind of propose more normal extension, northwest-southeast directed extension. So we had a couple of research questions that we thought with the seismic volume that we could address. And the first one was about how fault zones might accommodate developing volcanic centers, because we were able to image really quite nicely one of these fault zones that runs through the northwestern part of the data set. And we could trace that to a volcanic cone further in the south. And then secondly, like while we're doing that, then hopefully we can shed a little bit of light on this debate around the structural setting of the region and what the fault kinematics are there. So yeah, those are the kind of two things. So here's just another look at the data set, looking in from the southwest. And this is the Kolumbo fault zone that runs, it wasn't actually so well known from previous interpretations, but runs to the northwest of here's Kolumbo Volcano here, and strikes towards the northeast. And so the image there is a plan view looking down onto the fault zone in a coherency seismic attribute, which is just a way where we can highlight discontinuities in the data. So discontinuities have low coherency, and they, in this particular color stretch, they're black. So faults appear as black lines, or faults and fractures, anything that kind of breaks up the continuity of the reflections of the strata is black, and the continuous strata are white. So I just want to kind of take you through a few examples of the and just moving down through the data set. So at the moment, this is just a short transect across the fault from the northwest to the southeast on this blue line here. And you can see, so these are my interpretations of the normal faults here. And then the horizontal yellow line here is the level in the data set of this extracted seismic attribute. So that shows here at this particular level, we're just where this prominent normal fault here is getting up towards that time slice, and so we can see it here in the coherency attribute appearing like in the shallow part as a quite clearly defined fault. And so then I did quite a few different things with this. So interpreting the faults basically in 2D to generate Rose diagrams of the fault orientations, but also because the data in 3D, basically picking carefully the different fault segments throughout the data like in geological field mapping, that you basically can accumulate then a large amount of strikes and dips for these different faults, and then look at them and analyze them to get a feel for the stress field. So anyway, moving further down, that's at the top. If we move down, then we're kind of, I'll get back to this later, but this disturbed material here is, those are ignimbrites from the Minoan eruption, which have been drilled now. So there's drill sites on both sides of the fault. So we know that. And we know that this upper little unit here is the distal part of the pumice deposits that were laid down during the 1650 eruption of Kolumbo. So yeah, deposits from an eruption of Santorini, 1600 BC, and then 1650 AD deposits from more local Kolumbo sitting on top of it. Yeah, and so as we move down, you can see that the way that the fault zone is kind of evolving, or how we can see it at depth. We have the major normal fault strand here on the northwestern side, and then we've got these smaller conjugate fault sets that are dipping back in towards the main fault zone. So interpreted in there. And we keep moving down, and we can see this kind of, this rope structure with these, smaller scale. You can see them here. They're basically these normal faults in here that are, have accumulated significantly less offset than some of these larger southeast dipping structures. Yeah, and then so that gives us basically the opportunity. At the moment, I'm just showing one line here, vertical line, but going through the data set and mapping out all of these faults in detail gives us a family of faults from, or fault segments from this fault zone to basically analyze it. The other thing that we could do is try and get a view of the fault in 3D by interpreting a particular geological horizon, so across the data set. And so this red horizon here is the one that I chose to do that for. There was real difficulty. I spent a lot of time trying to figure out how that relates to the other side of the fault zone, and we don't really know yet. I think the drilling will tell us about how much throw there really is on that fault, and it could be quite a lot. But we've used this one here, and by basically picking that and then automatically picking it throughout the data set, then we get this the surface of a horizon that's been disrupted by the fault zone. And I think it's quite nice to give a bit more insight into what the fault's doing to the strata around it and how it's deforming. And so we can see quite clearly that we've got this major fault zone on the northwestern side that was really prominent throughout the data set. And there's another major fault that comes in further towards the down towards the southeast. And it's a typical, like a classic example of a relay ramp, which you have between normal faults. Basically, as the whole fault system grows, you have these smaller normal faults that accumulate strain, and they overlap with each other, and ultimately, as they accumulate more and more strain, they merge together into one prominent fault. And so you can see in this part here, we've got basically two relay ramps that are imaged just within a 3-kilometre length section of the fault, and the one deeper into the slide here, further away from us, if I get my mouse back here, has been pretty majorly breached as these two fault segments have merged with each other. And this one here is a little bit less mature. But anyway, yeah, so we can see what this looks like, and we have these. The relay ramps are complex in the way that they accommodate strain between these two faults that are both accommodating extensional strain, and then in between them you have various fault orientations basically coping with the complex interaction between these fault systems. And it's known from so 20 years ago there was from JR and Rick Simpson a nice study in the Taupo volcanic zone looking at focused vertical fluid flow in accommodation zones between segmented normal faults and in these overlapping regions. And on the right-hand side here is I mean, this really is a textbook image from Håkon Fossen, showing how in oil and gas migration and also in hydrothermal or just water migration or in magma migration, that fluids take advantage of these stepovers or these relay ramp structures. So after kind of, I mean, being aware of that, then we'd map things out, and this is where we could image the fault zone and the data that we've got. There are other older 2D seismic lines that we had access to, where we could trace the fault zone further down towards the southwest, and we can see that there's this small cone here on the seafloor, and it's sitting on top of the Kolumbo fault zone. So I imagine that if we'd had the time and we'd kind of doubled the length, the width of our 3D seismic volume, we would have been able to see the interactions between volcanism and the Kolumbo fault zone. But as it is, we have to say, okay, we know that this is the fault zone continuing down towards the southwest, and there's a little volcanic cone sitting right on top of it. And we kind of assume that may be taking advantage of one of these relay ramp regions where there's weakened crust and an opportunity for magma to kind of focus up through there. So that was a bit of an understanding about that interaction. And then the other thing about the understanding of the regional kinematics, I've just shown you an example from the Kolumbo fault zone, but we did the same thing in the two other regions of faulting within the data that we could find as well. And plotted over on the right here are just stereographic representations of those faults that we picked. So all of those thin gray curved lines are just the intersection of the fault with a bowl, if you will, like just to show what the dip of the fault is and the strike. So they're all more or less striking towards the northeast. They're dipping at about 60 degrees to the west or to the east. So we've got these conjugate faults. And if we take the poles to those planes and take a mean and then get the correlated plane to that mean pole, that basically gives us our best estimate of the strike direction of the intermediate principal stress, and perpendicular to that is the sigma 3 is the extension direction, which is these black arrows. So perpendicular to the yellow arcs here is the extensional direction from the geological evidence that we have of the faults in this region. And so groups 1 and 2 here, they're very similar in terms of a northwest-southeast trending extension. Down in group 3, it's a little bit more rotated around to the counterclockwise, but they very much look like pure normal faults extending in the northwest-southeast direction. And that agrees remarkably well as well with focal mechanisms from microseismicity. So there've been some OBS deployments that were back in around 2005 that were deployed around Kolumbo Volcano and recorded a lot of microseismicity. And from the larger events, they're able to determine the focal mechanism. And those are a couple of examples there as well of that. So that basically shows that magma migration beneath the volcano is taking advantage probably of microfractures or small structures that are also, kind of opening in agreement with the stress field that we predict. And that agrees with generally with the large earthquake as well, and with there's also previous studies on dikes and from Santorini and from fault systems as well. So yeah, it's pretty clear, I think, this kind of northwest-southeast extension, and we didn't really see any evidence for major kind of strike slip fault systems. So yeah, the region's undergoing northwest-southeast directed extension. and that agrees, like I said, with the microseismicity, with the large earthquake, with onshore mapping, and I didn't show there, but also with like regional kinematics from GPS data. It's quite diffuse in the area, but that also kind of suggests this northwest southeast orientation. Yeah, and it doesn't agree with those other studies of strike slip tectonics. And yeah, the Kolumbo fault zone, like I mentioned, it's characterized by these overlapping fault segments and relay ramps. And there's intense faulting within the relay ramps that can focus upward fluid flow. And we think that probably plays an important role in magma ascent at a small scale, like we showed with that smaller cone, but also possibly at a much larger scale within the rift system, you know, beyond the scale that we could investigate with the data that we collected. That's in case anybody's interested, the paper. And now I just want to move into, or I guess if there are any questions about that, or otherwise I'll just go straight into the volcanogenic tsunami part. Yeah.
One quick question. Is there any vertical exaggeration on those images?
Yeah, there is quite a bit.
The scale
yeah. Oh, so not on this one.
Yeah. So what's the
in here? That is about a couple of hundred. There's quite a bit of vertical exaggeration there. So the slopes here are that's about 13 degrees. The real slope of that of the flank there, and this one here is more about 17 degrees. So they're exaggerated, probably twice exaggeration, I guess here, roughly. But yeah. Sorry, I should have. There's not a vertical scale on there. Terrible. Yeah. Yes, Phil.
Query about the 956 earthquake. It's large magnitude, 7.7. What's known about that? And related to that, what's the thickness of the crust? You said it was extended, but what's the known thickness of crust, and what's known about that earthquake? Would you know that magnitude?
Those are good questions, Phil. I don't know. I mean, as you saw, it's a normal fault mechanism. I don't know how shallow that propagated up, and the crustal thickness there, is it like 20 maybe? I'm not sure. I have to check on that. Yeah.
Decent enough eruption.
Yeah, it's a big way for a normal. Yeah, in an extensional setting like that with thinned crust, it's a big earthquake. Yeah. We are going actually back there in later this year to actually survey around that, if it all works out, to collect a 3D volume around the rupture of that earthquake. Yeah, that's a good question. It's not really something I gave much thought to.
Question, Gareth?
Yeah.
Most of the faulting seems to be away from the main volcanic home. Is that just lack of data, or are there faults actually interacting where the main Kolumbo volcano actually?
Yeah, I think there certainly are, but it's mainly an imaging thing. So we collected the data set. Basically, the volcanic edifice takes up the entire width of the data volume. And to be able to image the faults nicely, you really want nice undisturbed strata where you can see all the offsets and everything. And that's just, it takes up the whole volume as that volcano. So it's destroyed much of it. Yeah, they're pretty hard to see because there's only 10 kilometre spacing between Kolumbo and Santorini. And some studies even suggest that the magma systems are joined. And so it's quite hard to kind of see much in between there. But there are, I didn't show in here, but we looked into some attributes directly beneath the crater, and there are some dikes that basically puncture through into the seafloor, and they are primarily also kind of oriented northeast, southwest. And there are, I find one of the maps here. I mean, this whole like alignment of all of these cones, they're all pretty well aligned towards the northeast as well. But there aren't there isn't much in the way of data. And originally we wanted to collect the data set northeast, southwest like that to go over all of those cones, but it's right at the boundary of the waters for Greece and Turkey, and so there's no way to get consent from Turkey to be able to collect the data there. So we had to squeeze it into the into the 12-mile zone. Yeah.
Okay.
Yeah.
What's your reasoning behind the different interpretations of the other papers that you have given and situations happening?
I'm not. So I think one of them that was based on GPS data. They have like really. So that is where you look at the relative movement of different GPS stations, but the signals are really, really weak in the central Aegean Sea there, and they've used gravity data, like completely different data sets to come to those conclusions. I'm not sure. Yeah, I mean, the bulk of the literature does actually kind of suggest that there's more of this normal fault mechanism there. It's just a couple of those more recent papers that being a bit more contentious, I guess, and throwing out some other ideas there. Yeah. I don't know. There could be some more component of strike slip motion there locally in different places where the faults kind of change orientation, and that kind of remains to be seen. But I think that whole region there is, pretty much just like an extensional rift system that's forming. Yeah. I'll climb into the but we can more questions afterwards as well, but get into the tsunami part. Okay, so yeah, this tsunami that was generated by the eruption of Kolumbo Volcano. What we know about that comes from eyewitness reports that were so historical eyewitness reports in some places. So, for example, in the southeast of Santorini, there were observations that the sea retreated before the wave came back in. And then there are also tsunami deposits that have been identified on the island of Eos and also in northern Santorini as well. And then a documentation of significant inundation at Mykonos as well. And in terms of the kind of geological chain of events, that could be more or less reconstructed as well, because of the way that things evolved over this 2 or 3 week period as the eruption was happening. So initially, what happened was there was these underwater eruptions with plumes coming through the water column, and pumice clasts and rafts rising up to the sea surface. And then they basically spread out with currents and with the wind. And after a certain amount of time as well, they become waterlogged, and then they sink back down and deposit on the seafloor. And so that continued over a period of a couple of weeks with this quite intense but not explosive eruption. And the volcano, then it's known also from eyewitness accounts that an island appeared. So it actually breached the sea surface, this pumice cone that was built up. And then not long after that, then there was the explosive eruption that caused the tsunami, and then the island disappeared. And now Kolumbo, so the highest part of the volcano, is 10 meters beneath the sea surface. So we collected data right over the top of that, and it was really close, obviously, to the hull of the ship and to the system. But 10 meters is where it is now. So that's the general kind of interpreted chain of events. And then there's a number of different kind of mechanisms that could contribute to a tsunami. So this is a summary here from a previous paper suggesting different possibilities. So an underwater explosion is an obvious candidate, and also a blast from an island, that's with the shock waves and coupling with the sea surface, generating waves on the sea surface as well, or the emplacement of pyroclastic flows deposited down the flanks of the volcano into the water. Caldera collapse is another completely different mechanism where you basically have rapid subsidence that the water level drops down and you create a tsunami and that effect, or some form of flank collapse failure, so a sub-aerial failure where sediment from the flank slips into the sea, or a submarine failure as well. So yeah, a lot of different candidates, and previously not too much understanding of what those mechanisms could have been. So looking at our data again here, so we're just kind of zooming in around the crater. Again here for scale. So if I say 0.2 to 0.7, that would be about 300 to 400 meters on the vertical scale, and then a kilometer there across. So it's highly vertically exaggerated here to show basically what the crater looks like, and what we think as well might have been the original kind of base of the crater where pumice deposits basically accumulated and filled up during the eruption as well. So we definitely know that we have as candidates the underwater explosion, possibly also the blast coupled with that as it was above the sea surface as well. What we didn't see throughout the data, but looking carefully, was any evidence for major structural ring faults or anything that would have allowed, like a caldera collapse mechanism to have generated the tsunami. So we don't think that that's a candidate. Also, what we know from the drilling but even before it was drilled, we were very confident that these were the Minoan deposits, the ignimbrites from the pyroclastic flow and placement into the ocean, as a very different seismic character for a start, but also AUV dives and samples from the wall of the crater have shown these layered pumice deposits here, basically making up the cone of the 1650 eruption. And so we didn't see any evidence around for ignimbrites from pyroclastic flow and placement. So I think that that's unlikely as well. What's not unlikely though is the involvement of some kind of failure of the flank of the volcano. We have all of this basically above here. This is all the 1650 deposits, these stratified pumice deposits, and we've got quite like incoherent and evidence in here for some kind of remobilization of the flank on the northwestern side of the volcano, and it's I think quite well characterized here that we have these. There are quite well pronounced compressional ridges as opposed to on the other side. Hopefully, it's obscured here from the view, but the other side of the volcano is very smooth and just a very smooth flank. Whereas on the northwestern side, there are these arcuate ridges in the seafloor, and then we have evidence for disturbed reflections that we interpret as folded strata above some kind of a detachment surface beneath that, and then also evidence for some slipping, like a partially exposed part of the glide plane from this collapse of the northwestern side of the volcano. So it's quite clear that there's been some kind of remobilization of the northwestern side of the flank, northwestern flank of the volcano. And these are just a couple of photos from dives, ROV dives from different parts of the crater, showing these really poorly consolidated, low density pumice deposits that basically make up the 1650 cone. And then there are dikes, was what I was mentioning before, Scott, there, that are basically protruding through the crater walls as well. Yeah, so my colleague then, Jens, he went back. There was a previous study that looked at an explosive source for the tsunami, basically based on the size of the crater, and assuming like a large amount of water displacement from of an explosion, that based on that volume of the crater that was ejected, and yeah, modeling that scenario basically to try and reproduce wave heights in these different places where there are eyewitness reports, or also tsunami deposits as well. And that particular paper was able to satisfy some of those observations, but there were a few where some of the details weren't really kind of taken into account. But anyway, this was kind of the starting point, was to do a numerical simulation of this explosion. So what Jens has basically done here for a bit of a sensitivity test of different volumes of an explosive source in a tsunami simulation, so just to see how the wave basically propagates with time. And I can show you hopefully here what that looks like. So on the left-hand side is basically just a small scale from 2 meters to -2 meters, showing the peak and the trough of the wave as it propagates from the explosive source at the volcano. So this explosive source, you basically just have to define a thickness of water column that instantaneously just pushes a wave out radially. And that was based on this other work also, and the volume there between 100 and 150, I think 175 meters. And yeah, and it propagates around. And then on the right-hand side here, we have the maximum wave height throughout the model space. And so we've got here these different locations on Mykonos and Ios, and then Parissa and Kamari down on the southeastern side of Santorini as well, where these observations have been made. And so in the model, he's basically set those up as virtual tide gauges to measure the wave height, the maximum wave height that comes in there. And so this is the black line here is showing the wave height at each of those locations. And whoops, sorry. So then we can kind of compare them to the geological record at each of those locations, or the eyewitness reports. And we can see, so here in the north of Santorini, 14-meter run up. So here is getting about 5 meters of run up. These things can all be tweaked a little bit by the size of the eruption that you use as the source, obviously. But some things that can't be reproduced by this with just a radially expanding wavefront is the initial sea retreat in the southeastern part of Santorini. So that didn't really work out, and also it was quite hard to get some of the higher magnitudes of wave height at these different places through the sensitivity testing that he did as well. So then the next thing that we wanted to investigate was what the potential influence could have been from a slide, basically from the destabilization of the flank. And so to do that, we had to have some kind of idea about the pre-slide topography. And so we recreated that based on the surfaces that we could map out in the data. And basically, because we knew that it had to go up to just above the sea surface to satisfy that observation that there was an island there, and using slopes from around the other parts of the volcano that haven't been disturbed to basically come up with this pre-slide topography, which is in the top left here. And then we have our interpretation of the detachment surface that the failure basically propagated along. So we have a before and an after idea of the slide, and then this is a geodynamic model basically of how this slide could propagate. The details of how that happened, the important parameters for that basically are the yield strength, so how easily that kind of fails and flows, and that kind of controls how quickly it propagates into the sea as well, and the density. And the density is known that this is extremely low density, these pumice deposits that have been, so that's the saturated density there of 1250 to 1500 kilograms per cubic meter. It's, you know, these pumice deposits that were laid down within the space of 2 weeks and haven't consolidated, and they haven't been sitting there long. So they're really weak, low density material. So yeah, played around with a parameter space for that and did lots of different sensitivity testing as well. And then you can probably barely see that, but that's basically showing this slide like propagating down the side of the volcano. And then you can use that, you can couple that in the tsunami simulation software that he was using, you can couple that to the water to have that as a tsunami source mechanism, basically. So that's what I'm showing here, and hopefully you can see, if you think back to what that looked like before, it's a completely different pattern, and it basically propagates out towards the northwest. The slide moved in that direction, and you have the strong wavefront peak followed by a trough propagating in that direction. But in the southwesterly direction, then you have a leading trough because of the dynamics of that basically slipping and leaving a cavity behind it, and that trough then propagating back towards the southeast. And so the good thing about that is then that these kind of curious observations of sea retreat that were made down in the southeast of Santorini can be satisfied by that mechanism, by something that's directed in one direction. So in the north of Santorini, from a landslide like this, it can generate like quite high run-ups. So you know, getting up towards the 14 meters that was documented from there. The initial sea retreat can be observed down here in the southeast, but the maximum wave height from there couldn't be. And I can't even read that now, but that is the 20 meter run up at EOS, so in the north, which, yeah, works pretty well with that landslide basically propagating towards the northwest. And then the other thing to test was basically an explosion and a slide. And there are different possibilities here, that you have an explosion first and that triggers the slide, or you have the slide that unroofs the magma system and causes the explosion. And you tried out both of those, but basically, I mean, if you have the explosion first, then you're only going to observe you're not going to observe any sea retreat down in the southeast. So you have to have the slope failure happening first to get those observations of initial sea retreat. And then, sorry, you have to have the slide for that, and then the explosion following that. And so, yeah, whoops, you can see where this is going, basically, that this kind of a scenario is one way of satisfying those different requisites from the both the geological record and from the eyewitness accounts. Yeah, obviously there's a lot of wiggle room in these kind of things in the way that you model them, but I think the key observation is that that sea retreat that can only be reproduced by something that's directional first. And so our reconstruction then basically of what we think kind of happened is that we had the beginning of this eruptive phase where the cone built up. So nothing new here. Basically, the ejection of all of the pumice moving up towards the sea surface, becoming saturated, settling back down on the seafloor, and over the period of a couple of weeks, establishing the cone. Well, I just realised this has taken much longer than I thought it would. So hope you're all with me still. Yeah, and then the slope failure happened, and basically the geometry of that, we can see that there's kind of up to 200 meters of sediment thickness above the magma chamber that would have been removed by that, and almost kind of instantaneously. And so for that thickness, that's and that density, that's about 3 megapascals of pressure, which is really significant for those kind of shallow depths. If you've got an ongoing eruption, to kind of lose really unroof a large amount of the confining pressure that's holding that, controlling that eruption to some degree. And so our volcanologists, co-authors on this, basically suggested that, with that large amount of depressurization, you have a massive increase in gas bubble size in the magma that's coming up. You also have water interactions with the more of it kind of being exposed to the water column. And ultimately that can then lead to a runaway explosive eruption and the large kaboom situation that then happened afterwards. So you have the directed tsunami first, the radial tsunami afterwards. And yeah, from the modeling, it was kind of always shown that there had to be at least kind of 3 minutes between the propagation of that slide and the eruption for that first wave to basically get there first and not be impacted by the radial tsunami that came afterwards. So how long that actually took, we have no idea, really, but it might have only been 5 minutes or something after the slide happened. Okay, so yeah, it was likely triggered by a combination of a landslide and an explosion. The landslide, it was really primed to fail, this thing. It was built up really quickly over 2 weeks, steep slopes, low density and low cohesion of this pumice material, and then it erupted. Then it slipped down, and that presumably then influenced the ongoing eruption and led to the catastrophic explosion. That's our story, at least, anyway. Yep. Thank you very much.
Have we got any questions? John?
Gareth, thanks. Gareth, they're working. The tsunami modelling, the results shown for the virtual tide gauges are wave height, but the comparison to the observations are run up, and there's quite a difference between those. You know, if any inundation was modelling, this is Jens who did the modelling, was it? Because you can get a lot bigger run up than your wave height.
Right. Yeah, obviously, I guess so. Yeah, running up over the topography. I don't think so. That's a good point. I think these are just looking at wave height. Yeah. Yeah. So a couple of those, I think the one from northern Santorini and then from EOS, they are tsunami deposits that are, so that's the run up, obviously. The wave height, some of that's also from the eyewitness stuff. But yeah, there'd be a bit of slop in that as well. Yeah. How much kind of difference can you get there? I guess it depends on the topography and the speed and everything. And yeah. I'll ask Jens.
Any other questions?
Yeah, really interesting. Thanks. Just one thing, I wonder.
Do you want the cube?
I speak a bit louder. I wondered in this scenario, do you actually see in the seismic data on top of the material that has slid,
more sedimentation from the volcanic activity, what you sort of would expect, if that sequence was correct?
I can repeat the question for people online. So you're asking if there's any evidence on top of the 1650 deposit that was remobilized, so the flank deposit. So any evidence of ongoing eruptive products on top of that. I don't think so, but it wouldn't have been much, I don't think anyway. I mean, that was kind of the end of towards the end of the process. So there was the 2 or 3 weeks of accumulation of the cone, and then we didn't see any evidence for undisturbed deposits on top of the slope on top of the deformed sediments. And I think that probably means that that slope failure happened at the end of the sequence, just before the catastrophic explosion. And then not much kind of deposit was deposited after that. I mean, there wasn't that ongoing effusive deposition.
Let's check and see if there's any
Oh, yeah. Oh, how do I see that? Do I need to stop share or probably?
Anybody online got a question? You can unmute yourself or pop something in the chat.
Yeah.
Cool. So any more questions? If not, then with Brian's got a question.
Gareth, was it P cable there is?
Yes. Yep. It was the P cable.
Simple question. Oh, Rick as well. Oh.
The question whether it was the GMRP cable that was being deployed.
And yes, it was. Yeah.
Cool. Okay, so I'd like to all of you join me in thanking Gareth for a very enlightening talk about the interactions between tectonic faulting and volcanism and tsunami. Really interesting talk to kick off the year's hopefully branch talks that we're rapidly trying to organise as a committee. So thank you very much, Gareth. Thank you.